Hello, I'm Rachel Pegley, and this is my Geoastria 5 major assignment presentation on Tasmania. Throughout this YouTube presentation, I will be describing the geological and tectonic movements throughout the evolution of Tasmania. Throughout geological history of the Earth, continents have moved and shifted in various ways. Through geological processes such as rifting, seafloor spreading and continental stretching, the continents we know today have continually come together and then separated. Firstly, starting as a supercontinent Rodinia, continental drift caused the separation and formation of Pangaea, Laurasia and Gondwanaland, and finally to how they are presently observed. Today, Tasmania is the name given to an Australian state which is separated from the mainland by sea. Bass Strait is the name of the area which separates the two land masses and was created throughout the movements of mainland Australia and Tasmania throughout history. Over 900 million years, Tasmania has evolved from a small fragment on the margin of Gondwanaland to how we know of it today. Tasmania has undergone many geological processes and tectonic movements throughout its geological history of over 900 million years. Evidence for such processes can be observed through the oldest exposed rocks on the landmass. A heavy history of sedimentation, volcanic processes, glaciations, faulting and folding, as well as continental collisions has shaped Tasmania to how it is observed in the present day. Most continental history can be traced back to the Proterozoic, yet the evidence may not always be available due to this era of time stretching from 2.5 billion years to 54 million years ago. Although there are still scientific methods which can extract data from this time to produce results and answers to how the geology, tectonic movements and environment may have been. In terms of the tectonic and geological history of Tasmania, the scientific community is fortunate enough to be dealing with some of the oldest rocks on the planet. Throughout history, Tasmania has experienced constant rising and retreating sea levels, volcanic activity, glaciations, uplift and constant folding and faulting of rock sequences. At the start, Tasmania was first part of the supercontinent Rodinia. Tasmania did not have the shape and isolation which it has today. It was a fragment of land that was attached to both Australia and Antarctica. Seymour, 2007, identifies that the oldest exposed rocks in Tasmania are found in the Tyne region. These rocks have been subjected to high-grade metamorphism and some are extremely deformed, yet others less so. The environment which would have been present was a shallow marine environment. Parks and Wildlife Services Tasmania highlight the evidence for this type of environment. It is believed that sediments such as mud, sand and silt were deposited into this environment and slowly transformed into rocks such as quartzites and schists. This explains why there were some rocks found within the Tyne region which were heavily deformed while others weren't. The Cambrian period marks the beginning of the Mesozoic era. This era is where most of the Tasmanian geology and tectonic history occurred. As mentioned before, the Tyne region is where the oldest rocks in Tasmania are located, although it wasn't until the early Cambrian that the Tyne orogeny was created. The tectonic sequence which allowed for this orogeny to exist was an arc-continental collision. Once this orogeny was formed, it hosted the initiation of many rapidly changing stress processes, which had different effects on rocks and minerals as well as faulting sequences. Volcanism was also present within the Cambrian period, the well-known Mount Reid volcanics. It is described that the Mount Reid volcanic sequence was an underwater volcanic system which was responsible also for a massive sulfide deposit on the western side of Tasmania. It is also believed that this underwater volcanic system was only occurring 500 metres below the Earth's surface. The geology found in this area includes rocks such as rhyolites, massive pumice breccias and andesites. The Ordovician period was between 500 and 435 million years ago, and Tasmania was still believed to be in a shallow, tropical marine environment. A passive margin connecting both the west and east sides of Tasmania has recently been discovered, dating back to the Ordovician. The geology of the passive margin is a more mafic oceanic crust underlying the eastern side and a silicic continental crust underlying the western half of Tasmania. It is believed that these two different geologies identify the transition from crust of Proterozoic continental origin to crust of Paleozoic oceanic origin. Could this be the passive margin? Other geology sequences found within the Ordovician are pebbly conglomerates and sandstone. The Silurian period saw the environment change from a warm tropical marine type to a much colder environment. The drop in the number of fossils found was evidence for this change. It is also believed that Tasmania was subjected to uplift, as well as abduction and increased amounts of unstable turbidity currents. Both deep and shallow marine units were identified from the Silurian, both containing silicic igneous rocks and mafic volcanic rocks. The Devonian period occurred between 410 and 360 million years ago. It is believed that very little sedimentation occurred during this period. This was due to the continuous folding and faulting sequences which were believed to be occurring during this period of time. It is thought that there were two major folding sequences during the Devonian, one trending north-northwest and the second northwest to west-northwest. Multiple dike sequences were also found dating back to the Devonian, which are believed to be also caused from the faulting sequences. Similar to the Devonian, the Carboniferous continued to host large granitic intrusions into rock series and groups. The late Carboniferous saw the reintroduction of deposition, which had stopped earlier. The deposits found from this period are of granites. These deposits have also been found within the 1.5 kilometre of deposits in the Tasmanian Basin, which has accumulated during the late Carboniferous and early Permian. Tasmanites can also be found dating back to the Carboniferous period in Tasmania. Former discoveries of Tasmanites within the Carboniferous period are evidence for certain geological sequences, which are thought to have happened during the formation of the Lachlan origin in the eastern part of Australia. The Permian period marks the end of the Paleozoic era. The Permian period was a host of glaciations which caused sea levels to drop and ice caps to cover the land. Due to this glacier period, the geology found from the Permian period is different to many other periods. The ice caps left dropstones within mudstone series, as well as tillites. Rivers which were flowing during this period laid down sandstones. It is also believed that during this period of time both Tasmania and eastern mainland Australia was subjected to uplift. The Jurassic period sees the beginning of the Mesozoic era. As mentioned above, the Permian period involved Tasmania being subjected to glaciations, as well as playing host to multiple ice caps across the island. During the Triassic, the geology and environment is recovering and evolving from this glacial environment to a warmer one. Due to the melting of ice caps, the sea level began to rise, as well as the creation of lakes and swamps within the island. Many of these swamps have led to the formation of coal peats, which have been used during the present day. Tasmania was heaved upwards during the Triassic, which led to the existing swamps and lakes being bordered by uplands. Geology present during the Jurassic period includes depositions of fluvial and sedimentary rocks. The Jurassic period sees the breakup of Gondwanaland. This affects Tasmania in terms of location and indirectly through geological processes to surrounding areas. The main geological feature of the Jurassic period within Tasmania is the abundance of dolerites. These dolerites give sufficient evidence for magmatism within the Mesozoic period. It is also believed that the dolerites were thrusted through weak areas of the Earth's crust and then intruded sideways. Today these dolerites can be seen in geological features such as the Organ Pipes, cliff tops on the Tasmania Peninsula, and the Cradle Mountain peaks. The Cretaceous period is the last period within the Mesozoic era. During this time, Antarctica and Australia were rapidly separating through rifting sequences. This separation between the two continental plates started to cause indirect geological features within Tasmania. The Tasman Sea also had a very active spreading movement which started the evolutions of basins surrounding Tasmania, such as Bass Basin. The Tasman Sea was formed through rifting along southern Australian mainland. This rifting is why the Bass Basin started formation. Another major geological feature that was produced during the Cretaceous period was the northwest striking Tamar Graben. This graben was formed during the Cretaceous period yet continued to collect sediment for many periods after. The Tamar Graben stretches from the Bass Basin to the Tasmanian island. The Tertiary period marks the beginning of a new geological era, the Cenozoic. Volcanics were present during this time, and there was approximately 30 volcanic eruptions during the Tertiary which caused miles of basaltic lava to flow into surrounding valleys. This geological event explains why there is such a large abundance of basaltic rocks dated back to the Tertiary period. Other geological events which occurred during this period was further uplifting of Tasmania due to continuous faulting sequences driven by a high heat flow, as well as major formations of horse and graben structures, such as the Derwent Graben on the southeast corner of Tasmania. The last era of the Cenozoic is the Quaternary era. During this time, Tasmania experienced Australia's last glacial maximum, which saw the formation of mountain glaciations which deposited many glacial deposits such as glacial tills. It is believed that Tasmania had 3 separate glaciation events: an ice cap event named the Milana, a valley glacier referred to as the Yolandi, and lastly, a cirque glacier known as the Margaret. Remnants of these glaciers can be seen today in Tasmania, in the Crater Lake and Dove Lake. Once the last glacial maximum had ceased, sea levels began to rise. This had a large effect on the Bassian Plain, which was the only connecting land between Tasmania and the mainland Australia. As the sea levels continued to rise, the Bassian Plain was lost under the seawater. This was now known as Bass Strait. This had major impacts on Aboriginal groups which had migrated across to Tasmania and were now stranded on the island, now to be identified as the Tasmanian Aboriginals. The last era of the Cenozoic is the Quaternary era. During this time, Tasmania experienced Australia's last glacial maximum, which saw the formation of mountain glaciations which deposited many glacial deposits such as glacial tills. It is believed that Tasmania had 3 separate glaciation events: an ice cap event named the Milana, a valley glacier referred to as the Yolandi, and lastly, a cirque glacier known as the Margaret. Remnants of these glaciers can be seen today in Tasmania, in the Crater Lake and Dove Lake. Once the last glacial maximum had ceased, sea levels began to rise. This had a large effect on the Bassian Plain, which was the only connecting land between Tasmania and the mainland Australia. As the sea levels continued to rise, the Bassian Plain was lost under the seawater. This was now known as Bass Strait. This had major impacts on Aboriginal groups which had migrated across to Tasmania and were now stranded on the island, now to be identified as the Tasmanian Aboriginals.